And now, Anand, video is allowed. Take it away, mate. You need to unmute yourself, Anand. There
All
we
right.
go. And I'm
Can you
going to
see me?
stop sharing mine so you can share your screen. Yeah,
All right. So can you see my screen now?
we can see your screen and we can hear you loud and clear.
All right. Uh, so thank you, CrowdField, for this amazing opportunity to talk about a topic that is very near and dear to my heart, a topic that I'm leading in the artificial lift space, and it's something that's very important and often neglected, but quite important root cause problem for artificial lift systems. And that is the topic of static gaseous liquid columns, sometimes alternatively called fluid levels. So we have these uh, static liquid columns, these fluid levels in all aspects of artificial lift systems, as opposed to natural lift systems, in different types of ESPs, rod pumps, um, gas lift, all different forms of gas lift, plunger lift. They're all systems with the static liquid columns, right? Gaseous static liquid columns, gas flowing through, net liquid rates of zero. And we also have this problem in gas wells as well. It's a critical problem there, including coal bed methane wells, where you have liquid columns that are hindering production. So this particular problem is well studied in chemical engineering literature. Um, but however, in petroleum, we're a little bit late to the game, and we still continue to use archaic, very poorly understood and easy to prove wrong rule of thumbs and methods to characterize and predict these static gaseous liquid columns and their pressure and gas fluid behaviors. So what I did, what I have been doing in industry for the last couple of years is exapting. That's my new favorite word to extract and adapt. Exapting chemical engineering knowledge uh, of gaseous static liquid columns, decades upon decades of really good work, good experiments, to our petroleum engineering applications. And I've made a significant discoveries. One of the major ones was the ability to calculate the digital fluid level from surface conditions. That has never been done before in the entire industry, and it's a very advanced transient flow simulation, and it's really a capability that opens the doors for many new ways of new levels of predictions, right, in artificial lift. And then what I like to do is to show a few of the high bottom line impact practical applications of this type of capability in full ESP multi-phase flow modeling. What I mean by that is both the annulus and casing simultaneously, and how every part interacts with each other. Rod pumps, pump intake pressure, fluid bottom pressure modeling, and some liquid loaded gas well modelings, both the onset and far beyond the onset when at different levels of loading and so on, right? And then in the end, I thought it would be interesting to bring everything together in a way. I'm a very practical person. I've moved away from academia for such a long time. I now see the benefit in just being able to simply demonstrate something that's intuitive to understand, and everybody can take away a learning that they can remember, right? So hopefully I'll get to that in the soon enough in the second half. So what you will learn new today is all about this whole capability, this digital fluid level capability. It is something that's not only useful for optimizing well production, but you can actually use it for detecting and diagnosing suboptimal equipment performance, as well as designing your equipment differently, right? And with this digital fluid level, which is one capability in combination with the bigger analytical simulation capability, we now have high fidelity simulations at the speed of milliseconds, right? Which is again something that's new and something that's never been done before. And that's what's in it for you. That's what you're going to get, that opportunity to run these simulations both on a human mode, for example, on an Excel desktop where there's no training required. Everybody can use Excel, as well as on edge because the size of this model is just 1.5 megabytes. It's a very small size code that can be run in robot mode, right? And of course, you can integrate this into your digital workflows and dashboards and so on. What that means for you is that you can, as a company, at the big scale, you can reduce costs significantly because the analytical multi-phase modeling requires less inputs than other types of models, right? And that way, lower inputs mean reduced costs, and you can model things a lot more quicker. This is just a simple comparison with the time it takes from start to finish, as quoted by our friends at Oxy. And you can bring down this time significantly. I'm just saying 10 minutes here, but really this is the simulations themselves takes milliseconds, right? So you're talking about at least at a minimum a 96% reduction in cost, and that's important, right? At the biggest level, of course, you are talking about digital product production optimization at scale, and that's where we have always wanted to go to as an industry and as a company. And you now have that capability to simulate all different aspects of artificial lift, digital fluid levels included, and that brings a whole different opportunity for your wells flowing pressure and rates flow management system. So why listen to me? Why learn with me? And what I like to say, why not just any old bloke that knows multi-phase flow? I have I would say quite a unique background in multi-phase flow, going all the way back. I've been trained by the best of the best in conventional multi-phase flow. But then I really took off a whole different path in multi-phase flow in creating the world's first wholly analytical model for multi-phase flow, for multi-phase flow, and that's breaking away from the need for lab-based correlations and closure relationships and so on, right? And I did that work at University of Texas at Austin. The research started there. There was a lot of proof of concept testing and industry validation for that period of time. And over the years, I started to gather also the world's largest database of multi-phase flow, all published data, the data from all the schools, all the research labs, and so on, right? And then recently, in 2018, I commercialized my first MVP, my product, MAPI, and version 1 to 6 was successful. But once we started to test it at the enterprise scale, I took it off the market in 2021 to improve it significantly. And now the next iteration of MAPI is going to be version 7, and it's truly a completely different product. We a lot of things that come to the market that quite frankly companies have no idea of what's coming. So not just digital fluid level, but a suite of software, digital multi-phase flow meter, digital well tests. So you don't need those well tests anymore in pipes and so on. Fluid pressure surveys. In other words, the idea is to go from a product to a change in industry. So I call it my OMG. And I've been publishing breakthroughs after breakthrough papers. So I think, especially in digital fluid level and fluid level type work, it's important to understand where we can go as an industry and where we have been. So let me talk a little bit about digital fluid levels in the past, and then I'll transition to the application, right? So let me state first a fact, and this fact is well known in everywhere else, apparently, other than petroleum engineering. But we know that digital fluid levels, through decades upon decades of experiments and really high-level research in chemical engineering, that they violently mix and they flow through liquids columns, right? And there's all sorts of behaviors that are well documented in the experimental literature of all sorts of different manners of recirculations and the tracking of the gas holder profiles along them. And when applied to the wells, we know that this is how your wells are flowing, right? The liquids and the gases are getting from your perps to your pumps in multi-phase flow. And it's partitioning in different ways, in complex ways, between your analyst and tubing. And there's a different amount of gas coming out here. And of course, these are live fluids. So there's an extra effect of just beyond downhole gas separation efficiency, but there's the extra effect of live fluids and so on. So this is what's actually happening. This is a fact. But this is not what we as petroleum engineers have been doing. So we know that there's a holder profile. We know that gas bubbles are rising, and we know that the average behaviors are rising. But we as an industry are stuck on very, very simplified calculations of one constant whole gas holdup, one constant pressure gradient, which, as you know, is impossible because as long as the gas holdup is changing, your pressure gradient is changing, right? And just hydrostatic calculations of very simple things, ignoring the gas below the pump and using a liquid gradient and liquid gradient and so on. So that that's where we have been, and that's where we are. And we can look at many different experiments of bubble column flow. I call it bubble column flow, but it's much more than that. There's slug column flow and there's churn column flow and other things. But we can look at a very simple experiment to demonstrate possibly an explanation of why we have been so bad in petroleum engineering. Because in petroleum engineering, you have to design the experiments properly, right? And what I've noticed in petroleum engineering experiments is that there's not enough length from the entrance to the measurements. And that's a critical factor. That's called flow development length. And if your flow development length is not sufficient, you will not be making measurements of the flow phenomena. Instead, you're going to be making measurements of something else, right? Of the actual experimental conditions, what we typically call inlet and entrance effects, right? And that's problematic, because that means every single data point from that experiment is wrong, right? And it's flawed. So this is a really good demonstration of a high quality data set. This is a CASI data set demonstrating this phenomenon. So what happened here is that the measurements were taken very close. And as you can see, they introduced gas from different directions, right? This is increasing and decreasing, different directions of increasing and decreasing gas rates. And they got a lot of confusion, a lot of theory of reproducibility, right? And the line here is the simulation, is the simulation of our work, which is based on a lot of physics. And then what they did is they increased the development length, and then they started to see sort of a trend. And this is where petroleum engineers are right now. And they believe that there's a separate sort of a behavior for bubble flow and a separate set of behavior for slug flow. But what if you did a correctly, if you did a correctly fully developed flow measurement in your system, which is a long distance between your entrance and your measurement, which is what we have in our wells, you realize that this behavior, this phenomenon is actually predictable, and it's predictable to a high degree, to high accuracy. And we have these sort of behaviors, this degree of predictability in all sorts of manners in the chemical engineering literature. To see many different experiments, just go to this paper, this SP paper, and you'll see what I'm talking about. This is just one particular paper. Now, if you are to apply the common petroleum engineering calculations for the average gas holder, because remember, in petroleum engineering, nobody actually calculates the gas evolution profile except myself, right? But if you were to actually apply these old correlations, including the new ones from modern companies such as Ecometer, you would find out that these correlations are far off. They have a constant overestimation of the amount of gas that's in your fluid column. And that's very significant. That's a very important finding, because what that means is you are overestimating the gas. That means you are overestimating the production. You're overestimating the production potential of the well. Your bottomhole pressures are artificially low. So you are saying that this well is actually more productive than it is. And that means you're leaving a lot of oil in the ground, right? So it has significant implications to your understanding of these systems. And this is just one experiment. There's several experiments in this original paper, right? This SP paper. And the reason why, in my opinion, the reason why they have always been this overestimation and these old methods is because these old methods are stuck in the world of constant pressure gradients, right? They want to claim that there's a constant pressure gradient downhole, and the reason why they want to do that is because it's a very simple calculation. It becomes a very simple calculation, right? As you know, pressure gradients are never straight, right? Unless it's a single phase liquid, and even that, the oil has varying densities and so on, right? But when you can only find constant pressure gradient type scenarios when you have a low gas volume fraction and the whole thing is more or less the same along the column, right? And then you tend to have less variation. And this is what older correlations have been using, right? And this used to work for the old wells, because in the old wells you have vertical wells, and they didn't have nearly the amount of gas that they have now, right? So these are old vertical wells with rat holes. In modern wells and conventional wells, or even wells with the pools far away from the pumps, you have a very sharp evolution of gas evolving along the column. And none of these things pressure gradient works, and you actually have to calculate the pressure gradient along the well, right? So let me prove that. Let me prove. We can take some examples of the past correlations, petroleum engineering correlations, and we can look at scenarios. So this is a real well, and we can look at scenarios where you have a low gas solar profile and therefore almost constant pressure gradient, and everybody's pretty much close there, right? And even in this is a published data set as well. Same sort of behavior. We know we can predict this because you pretty much only have liquids, right? However, the real excitement comes when you have a lot of gas. And this is a recent paper where you have a slug flow in your liquid column. And there's a then you start to see the inadequacies of the older petroleum engineering correlations, and they have a systematic under prediction of the gas of the pressure, right? Because they're overestimating the gas flow, and that's quite a big difference, right? And it's just this is just one example, but imagine if you're consistently overestimating the production potential, then you're going to be designing your equipment in a different way, right? So it has cascading effects to everything, down not just on the production side, but on the reservoir side as well, and how you manage your reservoirs, right? And the reason, you really got to dig down, right? The reason why even the modern correlations and the older correlations are give sort of the same predictions is because they haven't changed, right? This is Gilbert all the way in the 1950s. This is Archimedes correlation. All I did is reverse engineer the correlation and put an equation to it, and you can see they're pretty much the same equation, right? And remember, these equations, in case people don't know, the Archimedes original correlation is just based on 17 Midwestern wells. And you cannot apply that to everywhere else in the world where they have fluid levels, right? Or even in the US, right? So, we need to move beyond these old correlations and even beyond this sort of understanding, because this is a false understanding. It's unphysical. You don't have liquid columns, an oil only above your pump of water, because as long as gas is flowing there, everything will mix up, and that's intuitive, right? And of course, I'm going to show you that in this apparatus that I'm going to demonstrate. Even at atmospheric conditions, things mix up. Can you imagine when things are at high pressure and high temperature, right? And the reason why this has always been our understanding is not because it's real, it's because that's what we could have calculated back then, right? Now we have a much more better understanding of multiphase flow, so we can calculate things correctly. And also, it's how we used to operate wells and drill wells in the past. So, in the older days, you'd have these vertical wells. There'll be something called a rat hole, and you put your pumps, you sump your pump, but it was sumping your pump, right? Sometimes you put it here, sometimes you put it right at the curves, and you still have this. It's an entirely reasonable assumption and correct assumption. So you can say, all right, my water is going to separate, and I'm also going to show you that in one of these experiments as well, right? So this is the old way that we were working. Sometimes these pumps was a little bit up above the curves, and then we make some simplifying assumptions and so on. That is not the new way we drill wells. And in the new way, our pump is far away from our pumps, right? It's not just horizontal wells, but just wells in general, right? As long as you have deviation. And what you actually have is multiphase flow, right? Multiphase flow all over. You have multiphase flow here, you have multiphase flow in the recirculating liquid column. And you have fluid slipping in all parts of the well, and that's important, right? And when I mean all, because just like you have concurrent multiphase flow patterns, you have all of these flow patterns in your static liquid columns. And this is a new learning, right? Not many people actually know that. And we have experiments from chemical engineering to show that, right? Again, you have to go back into that literature, because they have the data, and you can have all these different. This is static liquid column flow, and you have all these different flow patterns. And of course, if you try to model these things with the existing correlations, even the modern tools, you are far off. You are very far off, and that's because there's the presumption, right, that you're only flowing through oil and you're only bubble flowing and so on. And again, this is not true, and that's the benefit of exacting chemical engineering technology to petroleum engineering, right? And there's a lot. This is just the tip of the iceberg. There's a lot of misunderstanding in the artificial lift world in general, right? There's people that don't believe that there's downward multi-phase flow, and they sort of believe that this is how your well actually flows, and you have this liquid flowing downwards and bubble going upwards. So of course, this is not your well at all. In a closed conduit, high pressure, high temperature conduit, you have multi-phase flow in all directions, whether it's in a four-way separator or any advanced separator, and you have to be able to model that, right? You cannot use inapplicable things like this. So in the next 5 or so minutes, I'd like to now change into applying all of that understanding into some high impact field applications. So here's in case you're wondering and you're looking at this on YouTube, all of these applications and detailed notes of these are on newspapers, right? I'll always list them over here, right? So this is an Apache well. It's a permanent horizontal well. And when we are now able to simulate, this is a simulation, this fluid level through the casing and match pump pressures. This is how your full profile of your well actually flows. As you know, sharp gradients, sharp changes in the gradients, your whole of gradients, and of course variable pressure gradients, right? This is a correct simulation of a casing side or ESP horizontal well. And we can of course apply this to any gas well that's loaded up, right? Now this is an important development because can you imagine if you use gray or some sort of single phase gas, your pressure, your bottom pressure will be here, but you're actually over here. It's you need to have a dual pressure gradient modeling in your gas wells, and you need to even know that you have a liquid level from your surface conditions. So this digital fluid level applied to gas wells is an important discovery and an important predictor, right? And we can compare them to fluid well surveys. This is a North America gas BP well. This is a marathon well, fluid level survey as well. This is the deep offshore gas well. And this was, this well was well described in the particular paper. And we were not, I was not only able to predict with the digital fluid level the dual pressure gradient, but I also predicted that soon afterwards the well would die. So this whole idea of gas well depth, predetermining the gas well depth and predicting it is now a solved problem. But those applications, as exciting as it was, is not nearly as exciting as the ESP problem, right? And in the ESP problem, it's a very, very difficult problem to solve properly. And I'm talking about ESP with matching algorithms and nodal analysis and so on. No. The real ESP problem is extremely complicated. The real ESP problem has different flow paths, right? You got multi-phase flow, it's splitting over here, and you need to calculate this. You can't just put a factor based on what someone is saying, right? And you need to understand the multi-phase flow in the tubing as well as in the casing, right? The liquid levels, because everything affects everything else. And sometimes these are changed up a little bit, but essentially for the main application, how this looks like is that you have a casing side simulation and you have a tubing side simulation, right? And your total gas is being split. It's being split into unknown ways. And this is the real value, right? You need to know what that split is. You really need to know, not back calculate, because if you're back calculating, you don't actually know. You're dependent on your model. And we have wells that actually have casing gas rate meters, so we know that we're back at we're simulating correctly, right? And one gas rate goes to the annulus and one gas rate goes to the tubing, and this whole thing is an interconnected system because there are different boundary conditions. There's a boundary condition here, there's a boundary condition here, and there's a boundary condition here. And this is what I talk about proactive production optimization. You can control the fluid level. And if you control the fluid level, you control the bottom of pressure, the pump intake pressure, and therefore you control the head of performance, right? So your pump performance is governed by all three, not just this one, not just the tubing flow rate, with what you think the gas in the tubing is, right? So this is a really, really powerful problem to simulate. Unfortunately, this particular problem was my most recent paper that I co-authored with Ovinted, right? So the multi-phase flow simulation we want to have for full ESP well modeling is we still want the basic data, wellhead data, PVT data, trajectory, and pump manufacturing curves. We do not want to rely on pump intake pressure. We want to be able to predict it because that's the goal, right? So less effort means less cost, right? Because to be able to design these wells and simulate it and operate them. And what we want is not just having information, we want transformation. We want to be able to simulate gaseous liquid levels from surface for pump intake pressure and FPHP. We want to be able to simulate the downhole gas separation efficiency, global gas split. So we can find out how, what are the best downhole gas separators to use in a particular scenario. And we also want to be able to simulate the pump intake pressure and pump discharge pressure so that we can quantify head degradation and we can find out whether head degradation is due to different effects, gas effects or otherwise, right? And this is not easy. This has never been done before except in the paper, except in my most recent paper, right? And it requires revolutionary technology way beyond matching algorithms and what we're accustomed to. And you can, how do you know that you're right? You can then compare your calculations of pump intake to the measure, right? So let's look at that process. Let's look at that process in a real Permian gas oil wells. This is an actual Ovintiv data set. The key difference here is that the casing gas rate was measured. The casing gas rate was put on this well just for this paper, this particular paper, right? 225247, right? And it's a typical high GR, high position volume practice horizontal well. And you are doing both simulations simultaneously, which again has never been done, right? So you have a tube inside simulation where you're simulating pump discharge pressure, pump intake pressure, and fluid bottle pressure. These are all your different pressure gradients that you have. You're also so you're getting all your pressures along your well. You're also simulating the casing side simulation, which has to be which determines your fluid level, right? So you know your fluid level, and you know your pump intake pressure is the same pump intake pressure from your tubing side simulation, right? And again, we see variable pressure gradients because your gas is evolving, your gas is changing, right, from a slug-in to a train and so on in these fluid levels, right? And when you are able to do that combined simulation, you are able to split the gas in different ways, right? So in this particular simulation, the gas was split total was about 500, and the simulated split was 422 and 78. And the simulated behavior of the pump itself was that at the upper levels of the pump, you had liquid. You didn't have any gas, right? You went back above bubble point, and then you came back out, right? And this was your predicted head degradation from this calculation, right? So you are downward thrusting, right? And when we compare this simulation to the measured casing gas rate, this is plenty good from a directionally right standpoint and from an engineering standpoint. And this demonstrates a whole new capability for calculating the net downhole gas separation efficiency. And keeping in mind that this gas separation efficiency includes the reforming gas through the tubing and casing path. It's a very, very advanced calculation, a first in the world calculation. So not only that, because it's a transient flow simulator, you can evaluate all of your local slug and flow characteristics just before your pump intake. So you can characterize the degree of churning, your degree of slugging, and you can do things with that, right? You can invent or create your own bubble breaker. You can put a cap tube. You can do anything that you want to condition the flow, or even understand the flow among different wells. So you can compare apples to apples when you're comparing wells. Now that's an interesting case, but this is in my opinion, a more interesting case because this is a high fluid level, high rate Permian well, in which case your pump is seeing almost all liquids, right? But at the same time, there's head degradation. So you have a large portion of your well is liquids. You're predicting everything as usual. You got a high fluid level, and in my opinion, this is the reason why. You remember the fluid level governs the behavior of the pump, right? And you are able to predict that even though your pump is seeing almost liquids, you still have a 47% head degradation, right? And you're upthrusting in this region. This could be this pump. Something is wrong with this pump, and it has nothing to do with gas interference. So you are proactively screening for problems. So this capability, allows us to say, beyond looking at the what we normally do, that having that high frequency real time data and making inferences and so on. we can look at things like this, very fast from a global standpoint, and understand what's going on, and confirm that, and confirm or deny that understanding, right? So in summary, I'm going to close up now because I need to go to the demo. But you can read more about all of what I've been talking about and far more examples in these papers, right? So what I'd like to do now is I would like to transition from my screen to the demo view. And let me know if you're seeing my whole, Alan, can you see my whole setup?
I can see your setup, mate. Yeah.
All right. So first things first, this is equipment that I had to modify. It took a little while to build, more than a weekend. But it's a tabletop experiment of digital fluid levels, and there's several things that we can use from a learning standpoint here, right? So first things first, what it is, it's 3 tubes. I'm going to use this tube. I've colored the water. The blue is the water. I'm going to use the water for them. They're going to use this tube to demonstrate basic things like bubble rise velocity and how liquid levels actually behave in terms of recirculation and so on. And then these two tubes here are filled with half with water, half with oil. And we're going to operate them like how we operated in the past. We're going to inject gas over here. This is your perforations, and this is going to be a modern well. And that's where that well, the reservoir is going to be far away from your pump, right? So you're far away from your pump, and we're going to see whether or not we have these liquid levels, these things nicely stacked, like how the books say, right? How the textbooks say, right? And again, just keep in mind, so that's the purpose of each tube. Keep in mind, this is a lab scale. This is atmospheric conditions, right? This is a simple pump, barely 50 feet per second, right? So this is a very low gas rate. Imagine if you had a high gas rate in a real well, right? That would be a completely different scenario, high pressures and so on, right? But this is these kind of fluid levels you have in your system. So let us look at let us turn on the system and see how this works.
Just a brief comment.
Yep.
You guys can change the view on your own meeting instance and switch from tile view to spotlight. You can see it bigger, but the recording will have the how we're looking at right now bigger anyway. But if you want to look at it bigger now, you can switch yourselves to a spotlight view from the tile view.
All right. So what we have here is a liquid column. I initially lighted this thing like a Christmas tree, but then I couldn't see anything in the camera. But you can see that we have we can control the flow rate of this system, and basically you have bubbles rising. We can bring it down to single bubbles. As you can see, the bubbles are rising at approximately, this is a 12-inch ruler. So let's say you're looking from here to here, and you're seeing 1/1000, right? 1/1000, 1/1000. So that makes a lot of sense because 1/1000 is 12 inches per second. And that's what we know from the chemical engineering literature, 30 centimeters per second, the same thing. That is what we've seen in different types of course, it changes according to the type of fluids and so on. But basically, the general observation is that, right? Now that immediately contradicts our 6-inch per second rule, because if you really understand where that 6-inch per second rule for a 1/4 inch bubble diameter came from, it's a completely arbitrary thing. It's a completely arbitrary thing for that was just generated for a liquid flow rate of 50 barrels per day in a 1-inch annulus, right? Believing that the gas rise velocity would need it to be 6 inches per second. So we know that that's not true, and you can do things like this too. And you can also disprove the rules of thumb, like 10 feet per second for annular flow. That's not true at all. It's actually 10 meters per second. So the thing to notice here is that we're generating these bubbles, and we can control the bubble size and so on, right? So let us do a couple of things. Let's increase this bubble flow from a nice stream, the single stream that it is right now, and let's go ahead and start a more violent stream of gas, right? So hopefully you're seeing a lot more action that's going on. As I increase this, you're going to see different things, right? Different things are going to appear. And this is what we call recirculating and structures, right? So your fluid column, and by the way, this is 4 inches. This is probably the same. This is almost the same as your 5.5 inch spacing. So now suddenly these small little bubbles um, are still smallish, a little bit bigger, but we're starting to see structures, right? And when you increase the gas fluid even more, these structures, there's an inner structure now, and there's an outer structure. And you can visually see. I mean, from my point of view, but you can probably almost see it. There's liquids coming downwards. There's bubbles coming downwards as well as going upwards, right? Now, here's the scenario now. A lot of the old understanding of research of liquid columns claim that they didn't recirculate at all. So what I did is I just bought these plastic fishes. It's a it's a plastic fish, right? That's way more or less dense than than the liquids, and I just wanted to see what these fishes would do in a liquid column, right? So right now the current understanding is that if you put chemicals on the casing side, they won't actually reach down your pump, right? They'll just sit on the top. So these fishes are like your chemicals, yeah. Now right away we see, well, they're kind of going downwards, but not really reaching the pump. Let's pretend this is your pump, right? But what will happen? What would happen if I increase the gas rate? If I increase the gas rate, now you start to see different behaviors, right? If you now you start to see a lot more recirculations, and you will see sometimes these fishes will actually go in different places, right? And it all depends on how much gas rate. So we can design these systems to recirculate in different ways, right? So let me just increase it a little bit so you can see a little bit more behavior, right? And by the way, there's another effect that I want you to notice here. Initially, we started at a liquid column about 4 inches below, and just because of the bubbles, the whole column rose, right? So the bubble size matters. If I used a different type of injector here, and I had large bubbles, it wouldn't rise at all. It just slip through, right? So bubble size matters, right? So now we see some behaviors here of these fishes going all the way down to the pump, right? So that's counterintuitive, isn't it? Why would this unless you had a good understanding of gaseous liquid columns, which is the nature of it, recycling nature, right? And again, this is a tiny gas rate compared to the gas rate that you have, right, in your wells. This is just an off the shelf pump, right, gas pump. So the point is here, you're going to have all of this structure, all of these recirculations that's going on inside of your systems, and you can design the systems to take advantage of those flow reversals, right? Those multiphase flow reversals. All right. So let me take off these guys. Let me take off these guys, and let's now shift attention to these other views, right? Now this middle tube represents the world where we had our reservoir here, right? And what we do is we'd either take our pump is placed right over here, and we're going to inject here. And what do you think will happen? What do you think will happen? Would the oil and water mix? So that's one of the questions that you can pause the video and kind of guess that, right? For those of you who will be watching YouTube. But for us that's watching now, it's intuitive to think that this is a very good, well-designed system, because if I inject here, what I expect to happen is that the gas is going to be there's only going to be an oil column above your pump, and the gas is going to go to the oil column alone, right? So let's see if that's the case. Let's see if So as you can see, there's no mixing, right? Again, this is a very low gas flow rate, and there's no mixing because this is effectively your inlet, right, for your inlet into your curves. This is the way that we have been drilling our old vertical wells with low gas, low GRL type older wells, right? And this works well. This sump pump type of thing works well, right? Now, let us now look at this guy, and this represents. Yeah, let me just turn this off. All right. All right. Now let's look at, right. Let's look at this guy. This is the big prize, right? In a real well, in a real horizontal well or a real vertical well, where your curves are far below, the current thinking in and you can ask, just go ask your production engineer what kind of calculations they do and how they do it and how they visually mentally visualize these liquid columns, is that it doesn't matter what's happening, right? This is your oil is going to always be above your your um your water due to density differences, right? And let's just ignore the gas, because why not, right? Now, as you can see, now that you've seen how things mix up, right? It's entirely reasonable, and again, pause the video if you think what's going to happen over here, right? It's entirely reasonable to think, well, wait a minute, if the gas is coming and you have all of that multiphase mixture coming in, won't everything just mix up? Isn't that just a obvious, intuitive type of thing to think? So let's see if that's what's going to happen, right? So remember, this was started off as a blue and yellow. And what does blue and yellow give you? Wouldn't you know it, right? Blue and yellow gives you green. And this will only get greener and greener as we have more mixing. Again, this is a very low flow rate uh, gas system. And as you can see, you're going to have multi-phase flow. You're going to have water. The water doesn't decide that it wants to stay. No, no, no. The density differences between oil and water is not that no way compared to the density difference between the gas and the oil and the gas and the water, right? So your water is going to go everywhere your oil is going to go, and that's the reason. This here is the very reason why you have high fluid levels in your wells, and that's why you can't operate them because you're not making the right calculations. You're only using an oil column above the pump, when clearly there's not an oil column above the pump because you are telling the water where to go. And that's not how multiphase flow behaves, right? The nature of multiphase flow is for fluids to slip and to mix. And we know that behavior now, but in the past, it was much more simpler to analyze things like this versus this, right? So the key message that I want you to walk away with here today is that we cannot use old technology and old understanding that was valid for the old wells, old vertical wells, for our high GR wells, or not even high GR, just wells that you have a multi-phase flow between your pumps and your reservoir, right? And you have to account for water intelligently. So my challenge to you is to go back to your production engineer, show them this video, challenge them, and ask them to make sure and update their calculations, make sure they don't use surface densities and constant pressure gradients, and ask them to really better predict what's going on, because I'm afraid if you don't do that, they're going to keep those calculations. And those calculations are going to be wrong, and you're going to have a wrong understanding of your pump intake pressures, and therefore your FBHPs, and therefore your reservoir and everything else, right? And you're not going to have a constant average gas holdup. No, you're going to have a evolving gas holdup, just like what you see. And it really doesn't matter where you put the pump because this is multi-phase flow. So that's an interesting. It's a very powerful statement. But as you can see, at atmospheric conditions, we can do these very simple experiments to demonstrate what we're seeing, right? And it doesn't matter. I can leave that running for the whole day. and it'll be green forever, right? Because there's another argument that says, well, over time at steady state conditions, they kind of partitions. Of course, that's not true because the gas is not lessening up in its fight. No, no, no. The gas is, in fact, the gas is getting more aggressive because more and more oil gas is coming out from the fluid itself, right? So we're just injecting here. But imagine if this was a live fluid, you'd have even more gas, right? So multiphase mixing, multiphase flow concepts are very important to your production optimization and to your artificial lift wells, and I dare say to your natural flowing wells as well. Because if you have very poor predictions in multiphase flow, uh, correlations, and your correlations are only tuned to pressure, you're not guaranteed to get anything else correct, right? So you still have the wrong velocities and the wrong trends, right? Because pressure is just one global macroscopic variable that you can get the same pressure from changing anything. You can change UR, you can change fluid properties, you can change fluidity, and you can even change a measured quantity such as diameter. And that's what's being done right now. What's being done right now is people are just changing variables haphazardly in an ad hoc sort of way just to match pressure. When truly what we need are more high fidelity, more models that honor trends, both experimental and field trends, and that are based on a different understanding. And that's where the analytical multiplication modeling kind of comes full circle. So I'm going to turn this off now. And with that, I'm going to transition back to my view. So give me 1 second. Let me load this. And let me get back to sharing my screen. Give me a second. All right. So can you see my screen, Alan?
We can see the screen. Yeah.
All right. So with that, I would like to thank you, all of you, for your attention and taking the time on a Thursday evening. I know how busy you can get. I'm a dad as well, and it's important to take advantage of these type of opportunities. And of course, thanks to CrowdField for the opportunity of discussing one of my favorite topics in the whole world, which is gaseous fluid levels. And with that, I'd
Now,
like to.
thank you, Anand. Thank you. A very engaging and fascinating presentation, of course. We have a few minutes. I'm going to open up the mic if somebody wants to ask a question. One of the questions in the chat was about the slide pack itself. I know I already said that this is going to be distributed via video on our YouTube channels and LinkedIn, but are you able to share any of this slide pack, Anand?
Of course, I
Yeah,
will. There's like I'm an open book. um,
great.
so I don't mind sharing this slide pack. What I suggest that you do is to connect with me on LinkedIn, and by connecting, you get my email. And once you get my email, you can request for the slide pack, and I'll send it to you.
Yeah, that's great to hear. Also, the option obviously is that I can distribute it to all the registered attendees to this webinar, if that
Yes,
simplifies things for you. So both options are valid.
yes,
Another question was about if you could explain again why is it that the production is overestimated with the conventional methods to bottom hole
yes,
pressure.
yes. Let me go back here. A lot of these slides were very busy. I'll give you that. But sometimes it takes a little bit of time, to read it and so on. So let me just talk about this one, right? So what we're seeing here, let's explain what we're seeing. Right? Let's break it down, right? What we're seeing here is that in your liquid level, right, in your gaseous liquid level, you got two options. One is to ignore the gas completely, which we know is a wrong calculation, and another is to account for some sort of average gas, right? So you have these different correlations. These correlations have a tendency, and it depends on which one, right, to overestimate the gas holdup inside of that liquid column. Now, what does that mean? What does that mean? So if you have a lot more gas, then your bottom hole pressure is going to be lower, not so? And when your bottom hole pressure is lower, you suddenly have a high drawdown. You have an artificially high drawdown. You have a huge producing potential. Your engineer is going back to your manager and saying, "Oh my God, we're doing so well here. We're pumping this well really, really well. Our pumps are working great, right?" And and therefore you're overestimating the producing potential. And you think, okay, we have got a great pump. Now let's do something with the pump. Let's change. Let's be more aggressive. And you can damage the pump equipment because of your feeling that you have a very good producing well, right? Okay, you want more oil. So the idea is that we need to have a and what when in reality what the scenario is, you have a lot less gas than what's there, and you have an oil that's sitting there that's remaining to be pumped, right? So you're leaving oil in the ground because of your belief, your calculation that this well is already maxed out. Does that make sense?
It does for sure. Anand, I have a question myself. Um, if I understood correctly, and correct me please, but the
Yes.
great breakthrough here is not only are you emphasizing the fact that unlike the conventional understanding where a dominant flow regime applies, what you're saying here is there's a bunch of flow regimes happening all at once, and therefore you're coming up with an alternative path to compute pressure losses along the well on account of those many flow regimes coexisting, which also includes these large-scale recirculations, which add additional pressure losses which were not accounted before in any of the conventional methods. That's what I'm seeing as the breakthrough here. Am I right or wrong in
Yes.
understanding that?
No, no, you're totally right. Because the wonderful thing about um, recirculations and the flow patterns and so on is that each one of these flow patterns and including their local behaviors have a macroscopic repeatable behavior, right? And that takes a long while to actually understand and get. But if we're not even accounting for them, so for example, if we don't even know that there is slug flow or churn flow in these liquid columns, then you don't even think about recirculations as a concept, right? So the ability to capture the flow patterns as well as their local behaviors, and more importantly, their macroscopic velocity and volume fraction resultant behaviors, because those are the things we can actually measure, and we can actually that actually participates in the pressure gradient calculation, right? That is the breakthrough. That is a breakthrough, and that's the whole pi fractional flow breakthrough, right? I mean, this was not a slide that I presented, but there's some extra materials here, and this is the whole idea. You can The pi fractional flow breakthrough is that you are interconnecting flow patterns in smooth, continuous, and differentiable analytical ways. That has never been done before. So now you're accounting for the flow patterns in these fluid levels, and including their local behaviors as well as their macroscopic behaviors, and that allows us to get a much more accurate understanding of the gas evolution profiles, all these different profiles, right? In the fluid columns, not just in the fluid columns, but when you have concurrent flow, and when you have countercurrent flow, which we haven't talked about as yet, but that's in the whole world of liquid loading.
And this large recirculation patterns, and is it a feature existing in all flow patterns, or are you introducing that
No,
effect as an additional flow pattern too?
no. So it turns out that every flow pattern is transient and has local small scale recirculation, right? So you have waves or different things. Like even in this thing that I'm looking at here, you got bubbles, but some of these bubbles are flowing downwards, right? As you saw, right? But the flow patterns that matter, that the recirculation matter, are things like chain flow, where these local liquid recirculations are very important, and you can design equipment to take advantage of those things, right? And those things are, and that's why chain flow is such a difficult flow pattern to model above all other flow patterns, right? Because and that's why the recirculating part of slug flow as well is so difficult to model. But the other flow patterns are, for the most part, the net of the flow is flowing in a particular direction. Yes, you are co-currently flowing, and you have positive liquid rates and positive gas rates, but the small scale local recirculation doesn't contribute as much as the macroscopic turbulence, right?
Fantastic. Um, is there anybody in the audience, guys, any of you would like to ask a question? It's 10
Yes,
o'clock over here. Go ahead.
I'll ask one. This is Smith Leggett at Texas Tech University. I was curious if you could comment on the implications of this work to plunger lift and intermittent gas lift systems.
Very important, yes. Two of my favorite topics again, right? So yes, we have been optimizing on plungers based on cycles, based on production, based on different things. but the opportunity to optimize plungers based on liquid levels, right? So if we understand our liquid levels in our plunger systems and where we are, where our plungers in those systems, first of all, quantifying the liquid levels in those plunger systems, matching those things with the global macroscopic rate, right? If we understand how they're forming, especially in the afterflow period. So the timing, right? The timing is critical. Those are opportunities for improvement of plunger timing optimization, right? In intermittent gas lift is all multi-phase flow, right? It's all static liquid columns, right? And the ability to understand that fallback, because it's a liquid column. Before you even get the opportunity for the pressure to remove that column, you have to understand the liquid column that's forming. So I would imagine that those people who are focusing on intermittent gas lift, this would be an incredibly important technology to take advantage of.
Thank you.
Fantastic. Anybody else, guys?
I've got one. Mike here. Hey, look, I've got a well that needs a velocity strength, a gas well that's got. Really
Mike, it seems you're talking. I can hear you very, very, very far away and low, mate.
Okay, don't worry about it. I'll pass. Sorry about that.
I think I don't know if it's just me, guys. Can you guys hear Mike asking?
No, just a vague little
Yeah.
noise.
Mike, unfortunately, your mic is playing games with you today, mate.
If you type it in the chat, maybe you can. I can't see the chat right now, but Alan could summarize it for me. Summarize the question.
Yeah. Would you like to ask on the chat, Mike, or?
I'm just putting it in the chat.
Velocity string for static gas wells.
What about velocity strings with static gas wells? If it will flow? So what's the question? Sorry.
This is
Velocity string for static gas well restart and lifting water out.
So once if you just put like I'll call it like a velocity string is like a capillary, right? You put a capillary, you'll get liquid rising up that capillary. But again, you will not get liquid evacuation all the way to the surface unless, of course, you exceed the critical velocity, right? And that goes back to your understanding of how these liquid. So it turns out that the critical velocity and the liquid level loading are linked, right, in a very strong way. So just by putting a capillary string or a small velocity string, you still would not, for a liquids loaded well, without adding any energy or without changing any energy, you're going to get those liquids rising up, but that liquids rising up because of the change in diameter is not the only force that's there, right? You got four forces, right? You got your convective inertial force, your viscous force, your buoyancy force, and the interfacial tension forces, right? So you need to actually have the enough momentum, enough well to actually cause the liquids rate to become a positive liquids rate, right? To rise. Otherwise, the just a change in diameter, which your velocity string in a static liquid column is, will act just as a capillary string or just as a straw in your glass full of water.
okay.
What are your thoughts on critical velocity from Turner?
Very bad. And don't take my thoughts on it. So go to this paper. I can prove it. Go to this paper, and I've looked at several different data sets of my own correlation compared to Turner, including at Texas Tech. So Texas Tech, Jim Lee used to work at Texas Tech, and there was a large set of experiments conducted just to quantify Turner, right, and how bad Turner was. That was the name of the paper. But I'll tell you. Give me a second. Let me show you the name of the paper. So Turner by the way, Turner and Coleman do not account for any diameter change whatsoever, right? The actual relationship or inclination, and they are based on one on one flow regime in your well, which is droplet behavior, right? So you need to have a full range liquid level critical gas velocity calculation, like my own correlation. It's the only full range calculation that accounts for a mixture of droplets, films, and everything in between, right? So for example, this is the paper, 209727. There's a large amount of comparisons of Turner and not just experimental work, but field work as well. And Turner was good for what it did. It's an explicit relationship. That's why everybody liked it. My equation is an explicit relationship too. But the difference is my equation accounts for diameter changes and accounts for inclination changes as part of the explicitness. And if applied correctly and applied to the correct pressures and temperatures, it is very accurate. And you can test that with a correct pressure and temperature, because the problem is different people use correlations and they use different hydraulics calculations to get the pressures and temperatures. And these pressures and temperatures then feed into these fluid properties, and the fluid properties then change the equation, right? They change the critical gas velocity equation. Then they walk away and say, oh my God, this critical gas equation didn't work. But the problem is your pressures and temperatures were wrong, right? So if you actually took correct pressures and temperatures, and you took measurements and you put it there, and you have a good understanding of the fluid properties, you get the right critical gas velocity calculation with my own model, called the Nagoo model.
Yeah, fantastic. I mean, we can spend another whole hour.
Yeah, I can talk
stuff, but
just
yeah,
critical gas velocity.
absolutely. Sheldon, you have your hand up. Did you have
Yeah,
another question?
I'll go ahead and send Anand a LinkedIn. I'll follow up on something with him there, just in the interest of time.
Okay.
All right.
All right, 7 minutes past. Thank you very much, everyone, for attending. Like I said before, this will be distributed via YouTube, and I'll liaise with Anand to circulate this back, or you can reach out to him directly. Thank you, Anand. That was absolutely fantastic, very engaging preso and a fascinating live demo. So thank you again for coming up, and thank you, everyone, for joining. Have a good day.
Thank you.
Thank you. See you guys.
Thank you.
Bye.
Bye.